Alright, welcome back. In this, we're going to go over Tosylates and Pyridine. I made a grand total of $0 in the past 28 days. In the next 5 minutes, you're going to know everything there is to know about tosylchloride and pyridines. So you may see this on an exam or practice problems or in a lecture. And I'm going to teach you this very quickly and very easily, faster than any other professor could. Because honestly, it's pretty easy. Alright, so we just finished with halides, alkyl halides, and doing substitution and elimination reactions. So this molecule should look familiar. We could do a normal substitution or elimination reaction right on this. But what if we had an alcohol instead? So something like this. We cannot do a normal substitution or elimination reaction. We have to do an extra step. Alcohols are poor leaving groups. Okay, that's something that a lot of people don't really understand or forget. Alcohols are terrible leaving groups, and the reason is because if this were to leave, it would not be stable. So think about, okay, let's do an example here. Pretend you're an alcoholic, or maybe you don't have to pretend, but okay. Guinness is one of my favorite beers to drink. Like when I go to a bar, I like to have a good cold glass of Guinness. After you drink it, say I had a few, right, and you're kind of tipsy or you're kind of drunk, right, and you leave the bar, you're not really stable, are you? You're not mentally stable or physically stable, right? I don't have good balance and I'm probably not in the best mental shape, right? You're not a really good leaving group. And think about this, if you're an alcoholic and you're at a bar, do you really want to leave that bar? Like I wouldn't, right, if I was one, but, So think about it like that. I know it's dumb, blah, 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 whatever. Okay. Hopefully this helps you remember. What a stupid example. Okay. Anyways, alcohols are poor leaving groups. So we need to convert it into something, then it can be a good leaving group. And that's exactly what we're going to do. Okay, so we need a way to convert alcohols to a good leaving group, and then we can do a substitution or elimination reaction. So we're still doing substitution elimination reactions, but now we're doing with alcohols. Now, alcohols, like I said, are poor leaving groups, so we have to do something to it. I don't think you really need to memorize all this, but I'm going to tell you it anyways, just in case. Helps you, it also helps you better understand what we're doing here. So you need 3 things. The first thing is you need an alcohol in your molecule, your starting molecule. You'll need something called tosylchloride, and you need something called pyridine. This is not pyrimidine, not like DNA, right? That's pyrimidine. This is pyridine, as in an organic chemistry reagent. So 2 different things. So what's going to be happening is we have an alcohol and we're going to put tosylchloride in a beaker. What will happen is the electrons on the oxygen, are going to attack the sulfur and kick out the chloride. All right. Then pyridine is going to come and steal a hydrogen from this. What we're going to get out of it is something called a tosylate group. You may see something like OTS. OTS is a great leaving group. A very, very good leaving group. So you may see something like this, OTS, on practice problems or tests, or on your lecture. OTS is basically like a halide. It has the same properties as halides, which are great leaving groups. Okay, so after we get OTS, then we can do our normal substitution elimination reaction just like normal. Just like we've been doing, nothing changes. We just need to convert the alcohol to tosylate. All right? So the big takeaway is we treat an alcohol with both tosylchloride, which is TsCl, and pyridine to get OTS, which is a great leaving group. All right? So you probably learned more than you did in the lecture by now, but we're going to add to it. Let's talk about configuration. This is very, very important. When you have the alcohol and you change it to OTS, the configuration stays the same. So wedges stay as wedges and dashes stay as dashes. Even though we are attacking the tosylchloride with the alcohol, the configuration stays the same. However, when you go from OTS and we do our substitution reaction, then the configuration changes from wedges to dashes or dashes to wedges, okay? So when we go from an alcohol directly to our substitution with tosylchloride in our our strong nucleophile, strong base, then we change the configuration. But if we're only going from the alcohol to OTS or tosylate, do not do a configuration change. All right, let's do some practice problems here. So what is the major and minor product for the reaction below? So we have a ring in OTS. Like I said, OTS is just a fancy looking halide. Even though it's not a halide, but just think about that. It's kind of like a halide. So a great leaving group. So what we really need to do is just do a normal substitution or elimination reaction depending on what the reagents are. So if this helps you, you can literally erase this and put chloride if you want, right? Same thing. I mean, don't do it on an exam, right? You're gonna get it wrong, but if it helps you remember, that's a way of doing it because it's literally the same thing, same properties. We have sodium ethoxide here. This is a strong base and a strong nucleophile. However, we have a secondary alkyl tosylate. This means that the nucleophilic reaction will be the minor product. The elimination will be the major. I'm not going to do the reaction here, but the double bond would form here, right? Because this is the alpha carbon, this is the beta carbon, this is the beta carbon. We could put the double bond here or here. I'm going to put it here. So the beta hydrogen's right here, right? I guess I'm kind of doing the reaction, but, you know. So we are left with these answers, right? And this is a normal substitution reaction where we do this, right? Keep this out, okay? So that's the answer. So it's like literally just a normal substitution elimination reaction, just like how we've been doing, right? It's just this, right? A tosyl group instead. Okay, so now we're on to something a little bit more difficult. Not difficult, but it's, it'll be fine. Okay, this may be the first time you're going to be seeing numbers, and you're going to be seeing a lot of this in organic chemistry. What do the numbers mean? It literally means step by step. This means that you're going to be doing this as step 1 and then this as step 2 at different times. Okay, so you're going to be showing the steps. Okay, that's what it really means. So the first step is you have tosyl chloride and pyridine. So we have an alcohol. So this means that we're going to convert it to OTS, right? Because when you have an alcohol and the first step is tosyl chloride and pyridine, we're going to be converting it to OTS, a tosylate group. So let's show the first step, right? So tosylate and pyridine, and we're just convert it to tosylate group. So the configuration stays the same. Now we are left with tert butoxide. Tert butoxide is sterically hindered. Since it's sterically hindered, and we do not have a primary alkyl tosylate, we will not be doing a substitution reaction. We will only be doing an elimination reaction. And on top of that, since we have a sterically hindered base, the Hoffman product is going to be the major product, and the Zaitsev will be the minor product. So we're going to have tert butoxide, and we're going to get this as our answers. Our major is the Hoffman, and then the minor is our Zaitsev, right? Because this is the less substituted carbon, alkene, right? And then this would be the major. All right, let's do the challenge problem. Tell me the reagents you would use to complete this reaction. Okay, so we have alcohol, and then we're getting rid of the alcohol and putting ethoxide here. So what do we need to do? Well, the first thing we need to do is get rid of the alcohol, right? Because we don't want the alcohol. We need to turn it into something else. And we're going to turn it into OTS. So the first thing we're going to do is add a number 1. Okay, it's too thick. A number 1. And we're going to add tosyl chloride and comma pyridine, PY. Okay, this would turn it into OTS. Now we have ethoxide here. And we have a double bond here. So this means that we are doing a substitution reaction because we're replacing something, right, with this, and we're doing an elimination reaction because you have a double bond there. Well, the only thing that we've learned that has ethoxide is sodium ethoxide. So we can do that. And that is a strong base and a strong nucleophile. OET. All right. And yeah, that'll be the answer because This is a primary alkyl tosylate. This means that the major product will be the substitution reaction, and then the minor product will be elimination reaction, and this is a strong base and strong nucleophile, so it'll do both. And that is it. If you found this video helpful, please like and subscribe. Until next time, later.